Hello and welcome to the first video in a course on computational number theory. In this course, I plan to go over the material you'd see in a cultural course on computational number theory, and I plan to go over as many topics as possible without getting into unnecessary details. So we'll see how it goes. We're gonna start off this course by talking about Pell's equation, which is a famous Diophantine equation. Uh, before we get into details and talk about how do we actually solve such an equation and what is it that we're really looking for here, let me just give you a little bit of history of where this came from. Let me give you a little bit of history of why people got interested in such an equation and how things evolved, like trying to solve it. So historically, mathematicians used to play with numbers, like number theorists used to play with numbers, and like a number theorist observed that like if we look at the fraction, if we look at the rational number 17 over 12, this turned out to be a good approximation of square root of 2. But then, like, people also played with numbers and noticed that the rational number 577 over 408 is actually also a good approximation of square root of 2. So there is something that is really happening here. It's not clear why, like, such a fraction, such a rational number would be a good approximation of square root of 2. So mathematicians noticed that if we look at an equation of the form x squared minus 2y squared equals to 1, and if we could find a solution to this equation with x and y being integers, positive integers, then we see that if we divide by y squared, what we have is x over y squared is let me just this is minus 2 equals to 1 over y squared, and this gives x over y is the square root of 2 plus 1 over y squared. And this right hand side is actually an approximation. You can think of it as an approximation of square root of 2. So like mathematicians noticed that a solution to the equation x squared minus 2y squared equals to 1 is actually like whenever you get a solution, the fraction x over y is going to be a good approximation of square root of 2. Okay, so this looks interesting. So before we continue talking about this equation and how to solve it, let me just give you a little bit of history. So this equation was falsely attributed to Pell, and the major work was done basically by Lagrange. So Lagrange proved that if you consider the equation x squared minus dy squared equals to 1, d non-square integer, positive integer, then this equation has a solution, has actually infinitely many solutions. So this thing was proved by Lagrange in 1773. So whenever you look at such an equation, Lagrange proved that this equation is going to have infinitely many solutions, infinitely many distinct integer solutions. And this is actually fascinating, because if you look at this, I mean, there's obviously a trivial solution. Like if you put x equals 1 and y equals 0, then that's definitely a solution, but that's just a trivial one. So there is some geometry here, like behind the scenes. Indian mathematicians played with this. So what we're really asking for here is like if you were to plot this, if you were to plot such an equation in the plane, it's actually a hyperbola. And what we're really asking for here is we're asking for points where like points on the grid where that intersects, or where the hyperbola intersects the grid, right? So we're asking for points, integer solutions on that hyperbola. So once you look at the geometry, it's gonna be no longer a surprise that infinitely many solutions. You should kind of feel that the existence of infinitely many solutions is 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 something reasonable to argue for, and this is what Lagrange could prove in 1773. So before we talk about the main way of solving Pell's equation, let us just let me just give a few definitions here, or let me just go back and define this for one more time. So Pell's equation, it's the equation x squared minus dy squared equals to 1. And what we're looking for is integer solutions. Like we want positive integers x and y for which this equality is satisfied. However, we want to assume that d is a positive non-squared integer. So this is actually crucial here. As an example, if you look at this equation, x squared minus 5y squared equals to 1, you'd see that x the tuple xy equals to 9, 4 is basically is a solution to this. But it's really highly non-trivial. It's really highly non-trivial why this particular tuple is a solution, right? And how can one even find such a solution? It's really highly non-trivial. So this is the purpose of this video. We're gonna give a method of finding the solution of Pell's equation. By I mean the fundamental solution of Pell's equation that we're gonna define in a few, using what's so-called continued fractions. So we're gonna go ahead and start working towards building the algorithm for finding such a solution. But before that, let us notice that the if you have Pell's equation, it can be written as follows. It can be written in this very nice way. And once we make this observation, we see that what we're really asking for here is, like, if you look at the square root of d, the set of elements a plus b, square root of d for a and b and z. If we look at this ring, we can actually define a norm here. We can define a norm. So we can define the a plus b square root of d by defining this to be a plus b square root of d times the conjugate of it, a minus b square root of d. So what's interesting about this is that a solution to Pell's equation can be read off from this equation. So solving this equation is equivalent to solving for an element of z square root of d of norm 1. In other words, what we're really trying to find is a unit of z square root of d. With a slight abuse of notation, we can so we call x plus y square root of d a solution of Pell's equation if the norm of that element is 1. So we just call it, this is an element of z square root of d. Okay, but this immediately brings up the issue of when we talk of a solution of Pell's equation, can we really talk of the solution of Pell's equation, or is it really biased to say that? Well, let's observe that if, so just a little note here, if x plus y square root of d is a solution to Pell's equation, then x plus y square root of d to the n is also a solution. And why is that? Well, the reason that is the case is because if you take the norm of that element, like of y square root of d to the n, this is by the multiplicativity of the norm, this is such, and this is just 1 to the n, which is 1. So like a unit, if you raise a unit to any positive power, is gonna also be a unit. And this thing, like if you factor it out by the binomial coefficient, binomial theorem, you can rewrite it as I don't know, some x prime plus y prime square root of d, and the x prime y prime now is a new tuple that satisfies Pell's equation. So like, can we really say something is like, so can we really talk of the solution of Pell's equation? Well, we can talk about something called the fundamental solution of Pell's equation. So we need to define this. We define the fundamental solution of Pell's equation to be the smallest positive solution in the ring of. So if we look at if we look at all these, so this is basically the element of z square root of d that is the smallest, right? If we omit the trivial solution, of course. So we pick an element of z square root of d that is the smallest, and we of course we ignore the trivial solution, and the smallest such an element, we call it the fundamental solution. All right, and it turned out any solution is going to be generated by that fundamental solution, in the sense that it's going to be some integer, some positive integer power of the fundamental solution. And one thing I want to note here is that the growth of this solution is really an exponential growth. We're gonna see this in this example. For example, if we're solving x squared minus 14 y squared equals to 1, then the tuple 15, 4 is a solution, and if we just square this, if we square this thing, let me write it this way. If we square it, we get this thing. If we just square this, right, let alone raising it to the 1000th power or whatever, if we just square it, look how big the numbers became. So the growth of this solution is exponential. And you can see this from the binomial theorem, because I mean, if you were to open this up, what would the xn be? For example, by the binomial theorem, the xn would be the sum from k equals 0 to n over 2, the floor of it, and choose 2k x1 to the n minus 2k, y1 to the 2k, d to the to the to the k. So like, just imagine raising this using, I don't know, using n, I don't know, 1000, then you'd be summing that power of d, let alone multiplying this by whatever the x1 and the y1 are. So this will make the solutions grow exponentially. You can derive the yn similarly. So now that we've motivated this whole thing, the question here is, how do we find the fundamental solution? So instead of so what we did now is that we started with this equation that has infinitely many solutions, and then we said, okay, so this we can talk of the solution if we define what's so-called a fundamental solution. So we can talk about the fundamental solution. So now if I tell you how to find the fundamental solution, you will get all the solutions for free, right? So let me now tell you how to find the fundamental solution. And for that, we need to use what's so-called continued diffraction method. So the motivation of this method is that is really what I mentioned at the beginning of the video. Whenever we're solving x squared minus dy squared equals to 1, if this is the case, then x over y is a good approximation. Let me call it a fair approximation. So it's a fair approximation of the square root of d. So whenever you hear the word approximation of an irrational number, there's something that clicks from I don't know, an undergraduate course in number theory, which is what's so-called continued diffractions. Because we know whenever we have a continued diffraction and we cut it, like we take a convergent of it, then that convergent is going to be just a rational number, and that rational number is like, if we take like a good convergent, then that rational number is going to be a good approximation of that irrational number that we're interested in approximating. So what we can do thus is start with this irrational number, which is the square root of d. Remember here, d is non-square, and we can apply the we can try to find the continued fraction for the square root of d. Okay, so it might be a good idea to write down some extra details here, because this is a little bit can be a little bit tricky. So let me just remind you of something. Let me just say algo, if we want to solve the Pell's equation. If you look at x squared minus dy squared equals to 1, and we're trying to find the fundamental solution, let me just say for algorithm for the or for finding the fundamental solution of this equation. Well, what you do is first find the continued fraction of square root of d. So once you find that, so let me just remind you here, it is always the case, like when we're working with a square root of this non-square number, non-square integer, the continued fraction of it, it's gonna be like always eventually, eventually it's gonna become periodic. So this is a standard number theoretic. It's an easy fact that one can check. So the continued fraction of square root of d is periodic. Like it's gonna be eventually periodic. And so the algorithm that I'm writing down now, I'm gonna write down the name of it here. So it's called, I guess, the Strassen algorithm. So this algorithm tells you to first find the continued fraction of square root of d, and let's say for example that the first period of this continued fraction is, let's write it as, so for example, let's say it's standard to use this notation, so I'm gonna use it, a0, a1, a2, and so on. So you found the continued fraction of square root of d, but then if we write it, since it's periodic, it can be written as, well, remember when we start with the the process, the algorithm for finding the continued fraction of an irrational number, we start by taking the floor of it. So a0 is really the floor of square root of d, and then you have some numbers coming here, and then you will have 2 times square root of n over here, and then it repeats. So you can write any continued fraction in this form, and in this periodic form. So it turns out that once you get this periodic form of the continued fraction, automatically you get the solution of Pell's equation. And that's super nice that you can just read it off from the this periodic form of the continued fraction. Okay, so I'm gonna give an example after I write this down, and it's gonna become clearer. But let me just mention here, let's see how to write this. So if we use AI over BI to denote the ith convergent, meaning you take you stop at the ith a, right, and you get the convergent. It turns out the fundamental solution to Pell's equation is going to be given by AP minus 1 BP minus 1 if P is even, and it's going to be A 2P minus 1 B 2P minus 1 if P is odd. So we're gonna see an example to make this clearer, but this is actually the Strassen algorithm. To solve Pell's equation, which is x squared minus dy squared equals to 1, what you have to do is find the continued fraction of, or write down the periodic continued fraction of square root of d. And once you do that, depending on whether P is even or odd, you're gonna stop either at the P minus 1th coefficient or at the 2P minus 1th coefficient. So let's take an example to make this clearer. So let's suppose we wanna find a solution of x squared minus 14 y squared equals to 1. So in order for us to find the solution of this Pell's equation, what we can do is we can start by finding the continued fraction of square root of 14. So remember, how do you generally find the continued fraction of alpha? So finding continued fraction of some real number alpha, well, the way you do it is by taking a 0 to be just the floor of alpha, and then you define alpha prime to be 1 over x minus, let me just use alpha here, so 1 over alpha minus a naught, and repeat on alpha prime. So this is how we find the continued fraction of a real number, right? So in other words, here what we're gonna have, the square root of 14 is just the floor of that, plus the difference, which is the square root of 14 minus the floor of that, and then this is the same as square root of 14 plus 1 over 1 over square root of 14 minus the floor of that, and this is our new alpha that we're gonna repeat the process on. And if you do it, what you're gonna get is you're gonna get this continued fraction. You're gonna get 3 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 6 plus 1 over in this case 1, and so on. So you see, we can write one more time, so 1 over 2 plus so on. So the first period is going to be here. This is the repeating pattern. So once you find the continued fraction of square root of 14, this is the periodic thing that we got. As you notice, this is just the floor of square root of 14, and this is just 2 times the floor of square root of 14. Just as we mentioned before, this is a standard fact that you can use. So now that we've found this, what we can do is we can actually stop at so this in our notation, this is the p minus 1th, right? So this is a1, this is a2, and this is a3, so it's basically a4 minus 1. So since p here is even, from the algorithm, we're gonna stop there, and we're gonna so maybe here a and b, so let me just use here alpha and beta. It was a bad notation. Yeah, this is my bad. Yeah, so we're gonna take the p minus 1th convergent to be the thing that gives the fundamental solution. In other words, if we take the p minus 1th convergent, take the 3rd convergent, in other words, we're gonna stop at this coefficient, and if we do that, this convergent is gonna give us this thing, 1 over 1. So we're gonna stop here, and if we do this, and if we expand this, it's gonna be 3 plus 1 over 1 plus 1/3, and this is 3 plus 1 over 4 third, and this is 3 plus 3 over 4, which is 15 over 4. So this convergent is 15 over 4, and this, from this we can read off the solution. X1 y1 is, x1 is going to be the numerator, and y1 is going to be the denominator. And this is how we get the solution of Pell's equation. So you can practice taking some d's and finding the continued fraction of square root of d, and stopping when it's periodic, and then depending on whether p is even or odd, you decide where to stop, which convergent to take, and you can then read off the fundamental solution. So I'm gonna stop here. I hope this wasn't quick, and we're gonna continue next talking about more important number theoretic algorithms.